Hello, and welcome to Virtual Class 15. Today is Thursday, May 21st. On the agenda for today is our food burning lab. We're going to look at the energy released when a sample of food, usually a snack food, is set on fire and that energy is transmitted to a sample of water. You'll also notice that on Wednesday of next week, we will be covering Hess's Law. That will be the last new content for this school year, believe it or not. And then finally, a week from then, on Wednesday, June 3rd, we will take our last exam on thermochemistry. Just a quick note, you'll notice that the days have shifted. So beginning next week, instead of meeting on Tuesdays and Thursdays, we'll meet on Wednesday and Friday for the last 2 weeks of school. I hope this doesn't confuse anyone, but it was a result of the Memorial Day holiday. So, for today, I'd like to begin by going out to Kevin, who is going to go over exactly what the setup for the lab would look like and show you one of these food samples burning. Take it away, Kevin. Okay, I'm here in the lab, and basically what I want to do is try and show you exactly what it would look like for one of these samples to burn. So if you'll notice, I currently have the setup for the Ritz cracker on the side here, and what you see is a paper clip holding the Ritz cracker, and then suspended above the Ritz cracker is an aluminum can, and that aluminum can contains a certain amount of water. So I'm going to light this sample on fire, so it's actually providing the activation energy for this sample. Now, once the sample is ignited, it will use the fat stored in the actual Ritz cracker to keep the reaction going. And then, of course, as the flame generates heat energy, that heat energy is going to go into the can, changing the temperature of the can. One of the most difficult things about this lab was getting some of the food samples to light. Ritz crackers were kind of difficult to light. Cheese curls were very easy to light. Potato chips were also very easy to light, and they tended to burn out quicker. The Ritz cracker actually was more difficult to light, but of course burned for a longer period of time. Those drips of fire that you see coming off of the Ritz cracker are actually oil and grease, which is being released as the Ritz cracker burns. And you can see the fire going directly up into the base of the can, and that of course is changing the temperature of the water inside the can, the measured amount of water inside the can. And we're actually using the idea that the energy given off by the Ritz cracker is going to be absorbed by the water inside of the can. Now, I mentioned this in the lab. Many of our calculations were off when we did this, and that's because so much of the energy is lost to other things. The paper clip, the surroundings, the can itself, anything that's not changing the temperature of the water is considered energy lost. And now you can see what it looks like after the reaction is complete. That charred remain of a Ritz cracker is actually the mass of the food that we'll obtain for afterward. All right, I hope that gives you a better sense of what this looks like. And then I'm going to send it back to the desk so that Kevin can talk about the calculation involved with this process. Thanks, Kevin. I had no idea there was so much energy, or grease, I should say, stored in a Ritz cracker. All right, what we're going to do now is we are going to look at a sample calculation involving that Ritz cracker. It's a stepwise procedure. I'm going to go through each step with you. What I would like you to do is pay careful attention, because you're going to be repeating this process 4 more times with the last 4 samples. So Kevin, take it away. Thanks, Kevin. So what we're going to do now is we're going to look at an entire sample calculation, and we're going to use the Ritz cracker. So based on the video that we just saw, what I'm going to do is I'll read through the calculation for you. I'll perform the calculation on the board behind me. And then what you're going to do is basically, well, you'll write down this one calculation in the spot on your handout, in the spot that I provided right here. And then when you're ready to do the remaining 4 calculations, you could do those on a separate sheet of paper. So I'm going to go step by step, and I'll use the numbering system in the calculation section to just kind of inform you of what calculation I'm doing. So the first one says to calculate the mass of the food burned for each sample. So to do this, I'm going to look at the mass of the food before burning and after burning, and that will get me a number which is the actual mass of the food that was burned during the process here. So we're going to take this step number 1. Our initial mass was 3.00 grams. Our final mass was 2.11 grams. So we have our mass of food burned as 0.99 grams. And again, this is for the Ritz cracker. The second question says, find the mass of water heated for each sample. So you're actually provided a volume of water. So you're going to use the density of water to convert. So if you have 100 milliliters of water and the density of water is 1 gram per 1 milliliter, you're going to wind up with 100 grams of water. And that's important because the amount of energy that is required to heat up a sample is dependent on the mass. Q equals mc delta T. We know that equation. Okay, by the way, all of these numbers that you're going to calculate should be recorded in your results table or table number 3. And it says that in the instructions. Question number 3 says, calculate the change in temperature of the water. So in our case, the temperature started off for this sample at 77.49 degrees Celsius and finished at 22.99 degrees Celsius. So that is a temperature change of 54.50 degrees Celsius. Calculation number 4. It says calculate the heat absorbed by the water using the equation. Again, as I mentioned earlier, this whole lab is based on the fact that the energy that is coming out of the food as it's burned is going directly into the can of water. Now, some of that energy is lost, which is why if we were doing this in lab, our answers would end up being much further off than you're going to find they are in this simulation. So if we look at the value for Q, or the equation for Q, so we have Q equals mCp delta T. And to kind of assist you in keeping these, keeping track of these, I did put them in order. So if you notice in your results table, the mass of water is the first thing. The specific heat of water, since it's the same, I've already filled that in for everyone, is 4.184. So we're going to have 100 grams times 4.184 joules per gram degrees Celsius times our change in temperature, which is 54.50 degrees Celsius. Now, we don't have to change the temperature into Kelvin because our constant also has units of Celsius in this case. So when we get that answer, it turns out to be 22,803 joules. 22,803 joules. Sounds like a whole lot. Obviously, the unit joule is incredibly small, so it is a lot of energy because there's a lot of fat and grease in there, but it's not astronomical. You're not going to light a light bulb with this. All right. So the next part, in question number 5, we're asked to convert our answer from number 4 into what are called nutritional calories. So nutritional calories are similar to regular calories, but they're more like a kilocalorie. So imagine 1,000 of the calories that we learned about last week. That would be equal to 1 kilocalorie, which is equal to 1 nutritional calorie. So this is a very simple process. So in order for you to convert your answer to calories, what you're going to do is you're going to take that 22,000, this is number 5 here, 22,803 joules. There are 4,184 joules in one of these nutritional calories. So what I do to differentiate it from the calories that we learned about last week is I write it with a capital C and then I underline that C. And that's just so we can differentiate between the two. So at this point, I get an answer of 5.450 nutritional calories. In step 6, what we have to do is now find the calories per gram of food, because that's what we're going to use as our basis for comparison. When we get our final answer, we're actually going to compare it to the numbers that are found on the nutritional label. And that is the information in table 2 of your lab. So what we're going to do here is we're going to take that 5.450 450 nutritional calories, and I'm going to divide that by the mass of the food. So for this sample, obviously this is going to be different for every sample, but for this sample that's coming from up here, we have 0.99 grams. So that winds up giving us a value of 5.5, and I lost significant figures there, that's fine, 5.5 calories per gram of food. So a subtle change in this case because we used 1 gram of food, or approximately 1 gram of food, but depending on how much food you use, that number could change more. And then finally, the last thing that we're going to do is calculate our percent error. So this is our experimental value. That's the value that we got by doing the experiment. And we're going to compare that to the accepted values. And the accepted values are in the last row of table number 2. So if you remember, for percent error, it is equal to our experimental value minus our accepted value divided by our accepted value times 100. So our experimental value is 5.5 calories per gram. Obviously, absolute value sign around that. Our accepted value is just 5 calories per gram. So we're going to put that both over here and on the bottom. And in this case, we're going to multiply by 100. And in this case, we wind up with a percent error of 10%. So in a normal lab, I would say a 10% error is really high. In this lab, a 10% error is excellent because so much energy is actually lost during this process to the surrounding air, to the paper clip that was holding the Ritz cracker, to the aluminum can itself. Remember, any energy that's not going directly into the water is not registering because only the water temperature is being measured. We're not measuring the change in temperature of the paper clip or the can or the iron ring or anywhere else that energy went. All right, so I hope this calculation is clear. If not, I will be available on Zoom at 10 a.m. and 12 p.m. if you have any questions. Otherwise, I hope everyone has a great Memorial Day weekend. I'm going to send it over to the desk, and Kevin will take us out. Thank you. And there you have it. So your homework assignment for this weekend is to finish up the calculations for that lab. Again, it shouldn't take that long. It's a lot of little steps, but you should be able to do that quite easily now that you saw what you need to do. Please complete that on a separate sheet of paper and attach it to or scan it to the back of your lab when you submit it. I hope everyone has a great Memorial Day weekend. Please get outside and try and take in some fresh air and just move around. I hope everyone is doing very well and that you're all staying safe. It's most important. All right, until next time, I'll see you guys. Thank you.